So this is one of the more fun chapters of our course. It's on dark matter. It's something that I've also spent many years researching back in the good old days in the 90s with some pretty cool people like Joel Premack and Sandy Faber up at UC Santa Cruz. And so I know a fair amount about this. So let's begin. Dark matter. And don't ask me what it is yet, because we're going to leave that as a mystery. In fact, for maybe longer than you'd like, but anyway, that's what we're going to do. So the first evidence that dark matter might be out there, you could almost call it conceptual. You could ask, well, why should nature be so accommodating as to make everything easily accessible to our rather limited extent of eyeballs and even detectors? And so maybe there could be stuff out there that we don't know about. And there's this guy, a little unfortunate actually, Fritz Zwicky, who is a bit of a cranky guy, but also a very brilliant guy. Early in the 20th century, worked at Caltech, and he studied the Coma cluster. This is the richest large cluster of galaxies. It's much further away than the Virgo cluster, but it's also much richer. Virgo cluster is a pretty good cluster too, but it's about 1/3 of the distance, I think, as the Coma cluster. And the idea, there's the Coma cluster. These are the two giant cannibal galaxies that are in the middle of the Coma cluster. So these are merger products, just to do a little micro review. These are merger products of other galaxies. Probably 4, 5, 6, 7 different galaxies have all blurred together to make these two guys. Someday these two guys are probably going to wind up together and make a bigger guy in here. A couple of things to notice about the Virgo cluster. Look at how many ellipticals there are. Yeah, ellipticals are, among the bright galaxies, ellipticals are much less common than are spirals. But in rich clusters, collisions are more common, and so we get lots more merger products, and merger products, after they settle down, they become ellipticals. That's a star, not a galaxy. You can tell because of the four-pointed pattern there. That's diffraction around the secondary mirror support. Okay, so what he did with the Virgo cluster was he used the Mount Wilson telescope, the 100-inch Hooker telescope, and he measured the velocity that these galaxies were moving. So he took spectra, which is a very painstaking process on old glass plates back in the old days, and tried to find their absorption lines and then measure the Doppler effect, and so he could measure their velocities. Now the Coma cluster is pretty rich, and we're only seeing the inner part here. And when you zoom back and you look at the whole thing, you can tell that it is very concentrated in here, and the concentration of the cluster goes out. As you go out, goes less and less. And so the cluster looks what we say is dynamically relaxed, or at least it's gone a long ways towards that. So what that means is that each of the galaxies have probably been swung around in square dance fashion at least once or twice. And so the cluster has achieved a kind of relatively close steady state look to it. And that's important because what that means is that then you can measure the velocities and you can measure the size of the cluster, and that's going to tell you how much mass there must be to be swinging those galaxies around at the velocities that you see, and yet have those galaxies be spread out enough into the size that you see. So if you take Kepler's third law, and again I keep telling you that's the most valuable law in astronomy, it allows us to measure the masses of things. And if you take Kepler's third law and you do some statistics with it, we're not going to have elliptical orbits in a situation like this. We don't have a two-body situation. We have a 1,000-body or 2,000-body situation. But if you use Kepler's third law and you do some math with some statistics, then you can arrive at a reformulation that's called the virial theorem. And so one way to talk about this cluster is to say this cluster is virialized. The virial theorem. I think I might use this word later, but in case I don't, I'm going to write it out for you. Virial. Kind of like viral, but not. It's virial. The virial theorem. And the virial theorem is an easy relationship between the size, the average speed, and the squared velocity of the galaxies and the mass that's inside. And from the virial theorem, he calculated how much mass there was in this cluster. Then there's another way to figure out how much mass is in the cluster. You could just look at how bright these were, and you could look at the color of them, and thereby get an idea of their stellar population, knowing they're dominated by red giants, and having an idea of the mass of red giants and other stars. You get a statistical representation, decent guess of the stellar population, and you calculate how much mass there is in stars. Stars look like they're the dominant component of galaxies, and even if you throw in another factor of 50 or 70 or another maybe even 100% for hot gas that might be out there, you get an idea of how much mass there is in these clusters. And when he compared the two, he was amazed because they didn't match at all. The velocities of these galaxies was so fast that there must be, 10, 15, 100 times. I mean, it depends on the assumptions as to the distance, and he frankly didn't know the distance very well. But what you can say is that the mass was way more than you would get with just stars. So the idea of dark matter was born. But the problem was, this was Crazy Fritz who was telling us this, and it was way back in the 1930s. He was really way ahead of his time. And it wasn't that astronomers didn't believe him, because he had a reputation for being cranky and maybe a little rude sometimes, but he actually was a pretty smart fellow. But it was really before the time that we had enough technology to really check this out. So that knowledge just kind of sat there for a while. It sat there until we had new detectors that came along, and we had new astronomers come along, and so that's where we're going to go next. But anyway, this is just to give you time to read this slide here. You do have to admit that claiming that the Coma cluster has 10 times or even 160, depending on your assumptions, more mass than you can see is a pretty extraordinary claim for the 1930s. Extraordinary claims require extraordinary evidence. Sagan's corollary to Occam's razor, talked about in Chapter 0. So, what kind of extraordinary evidence could we possibly amass? Well, along comes Vera Rubin at the Carnegie Institute and her graduate students. And Vera Rubin, one of the top astronomers of the 20th century, she's just been honored with having her name put on one of the new space telescopes that's going out there. Oh my God! I think it's one of the space telescopes. Might be one of the new monster scopes that's going up. Anyway, the Vera Rubin telescope is going to be doing fantastic work, just like she did. And she came along with Kent Ford, and what they did is they measured the speed of the rotation of spiral galaxies. So the neat thing about spiral galaxies is that the stars all move in roughly circular orbits. And so you can get an idea of the mass that is inside that orbit by just using, again, a reformulation of Kepler's third law. Remember, one of the neat properties of gravity that we learned, and it's true in general relativity as well as in Newtonian gravity. And Newtonian gravity is just fine here for this purpose. We don't really need general relativity. But you get all the mass that's outside of your circular orbit in a spherically distributed mass pulls on you equally in all directions and therefore can be neglected. So what you get by mapping the velocity of stars that are at this distance, and then at this distance, and then at this distance, and then this distance, and so forth, and you just keep getting velocity measurements all the way out, and then you can get an idea of how much mass there is inside this orbit, and then that orbit, and then that orbit. And so what you get is what we call a rotation curve. And so that's what these curves are. So what would you expect if galaxies are what you see is what you get? So we're looking here at M33, the little dwarf galaxy, or not really dwarf, but kind of a middling spiral galaxy in our own local group. So, of course, it's pretty bright inside, and it's pretty dense. There's a lot of stars. But if you forget about the black hole in the middle, which we already decided was scary, but also pretty minor in comparison to the total mass of the galaxy. So without loss of what I'm trying to get across here, we can just throw it away. Then if you look at orbits that are really in close, then you're encompassing almost no mass. So the velocity you'd expect would start out at 0, the rotation velocity, and then rapidly go up because you're encompassing more and more mass rapidly because there is so much density of stars in here. And then when you get about 2/3 of the way out, then you've pretty much reached a tipping point where now the amount of additional mass, the amount of additional stars that you're including as you go out further, is offset by the fact that you're getting farther away from it all. And when you get farther away from it all, then you know gravity gets weaker. So the generic rotation curve that you would expect, that's what I'm leading up to, is this. You'd expect the rotation curve to rise rapidly, reach a peak, and then kind of gradually fall off. Now, it wouldn't fall off exactly like Kepler's law does in our solar system, because in our solar system, essentially all the mass is right at the center where the sun is. In a galaxy, it's much more distributed, even if you just think of the stars. But what was amazing that Vera Rubin found with spiral galaxies is that the rotation curve does not drop. In fact, for this particular galaxy, it continues to go up. And in all the galaxies that she looked at, it went up and then it either stayed flat or it continued to go up, and we did not see these falling rotation curves that we expected. So the general term that has kind of come to be used for this phenomenon is called flat rotation curves, because a lot of them look kind of flat. I think I might have a graph on that. Yeah, okay. So the disk, which is made up of mostly stars and gas and dust, shows the kind of curve that you'd expect. But the halo, the spherical component, never comes down. And the total does this. So this is telling us that, well, and then here's real data, old data, but good data. And again, so Vera did this for a lot of spiral galaxies. And even though this was back in the 1970s, and yes, I'd like to think that astronomy was better than most fields in recognizing the, the brilliance of women. It was still lagging somewhat, and she then probably felt she had to work triply hard to get this good work totally recognized. So she did a lot of galaxies, is my point. She looked at a lot of spiral galaxies. She had good instrumentation, reticons and CCD chips later that could electronically measure the spectra much better than could glass plates, as we talked about in Chapter 6. And so she was able to get data that was hard to get before. And there you go, flat rotation curves. Okay, so that is indicating there is dark matter inside individual galaxies, as well as, according to Fritz Zwicky, inside these clusters of galaxies. So now, here in the 60s and 70s and later, we also had new access to new wavelengths. We had radio waves first, and then later we had X-ray telescopes that could go up. And so let's think about how we could measure the mass of a cluster of galaxies using these two phenomena. And even a third here, gravitational lensing. So let's think about X-rays. Okay, there is an X-ray picture of the Coma cluster. And that's the purple, so it's color-coded. Obviously, you can't see X-rays, so you have to color-code it. But what you're seeing here is dense and or hot, both kind of convolved together here to make more X-ray emission in the middle, and then the X-ray emission falls off as you go out. And you also see some X-ray emission concentrated around some of the brighter galaxies that are ellipticals, actually, if you look at their morphology. And now think about how that hot gas is going to distribute itself. Oh, so by the way, X-rays, it comes from gas that's of order 1,000,000 degrees. If you look at the velocities that Fritz Zwicky was measuring for the Coma cluster, the velocities were on the order of 1,000 kilometers per second, pretty fast. If you plug that into our formula for 1/2 mv squared equals 3/2 kt, then you end up with a corresponding velocity. Well, the velocity of 1,000 kilometers per second gives you temperatures of order 1,000,000 degrees, and that's in the X-ray part of the spectrum. So you would expect if there was gas out there in this cluster, the gas is getting blended up by the blades of all these galaxies, moving through the cluster, stirring it up, heating it up to 1,000,000 degrees. Very thin gas, not super dense gas, but very thin, but still, that's pretty hot, and it's enough to give off X-rays. The extent of the X-rays and the temperature of the X-rays is a completely independent means to calculate how much mass there must be to heat up the gas to this level and have it extend out in this way. It's not really Kepler's third law. It's using a very different thing, but it's kind of related. You're again looking at temperature now as a proxy for velocity, essentially. But you're still using the size of the cluster as part of your diagnostic. Okay, now we're looking at another cluster of galaxies. This is not the Coma cluster. And now we're using a totally different technique, which we haven't talked about before. This is gravitational lensing. So we learned that one of the consequences and one of the demonstrations of the truth of Einstein's law of gravity was that light will bend when it goes through a gravitational field. And it will bend in the direction of the increase in gravitational mass. And so what that means is if you have a cluster, the foreground cluster here is all these fuzzy blobs of orange and yellow, and then the blue things are actually images of galaxies that are roughly twice as far away. Another cluster that's way in back. And what you want to notice is that the direction of these images, the orientation of these images, is showing a kind of, well, it's like looking through the bottom of a Coke bottle, okay? Coke bottle bottom effect. So these arcs, these gravitational lensed arcs, are all in the direction, the perpendicular to them goes towards the center of the gravitation that is causing the lensing. And by measuring the optics, you can essentially develop some laws of optics based on general relativity as to how background objects should be distorted as they go through this foreground gravitational field. And by using those laws of optics and inverting them, then you can figure out how much mass there has to be to cause that amount of lensing. That's the bottom line. Here's another cluster, and it's a little better resolution. And again, you see arcs and arcs and arcs everywhere. Those are all background galaxies that are being gravitationally lensed. Excuse me. So it's another way to get the mass. And it confirms what Zwicky was finding. It confirms what the X-rays are finding. It's confirming what Vera Rubin was finding, and it's beginning to look like pretty extraordinary evidence to back up a pretty extraordinary claim, that the universe is dominated by something that we can't see. And so we have dark matter. There's dark matter in elliptical galaxies also. So how would you do that? Now remember what an elliptical galaxy is. It's really like a big swarm of bees, hundreds of billions of bees that are all buzzing around in a random way. So they're not going around in circular orbits, so you can't use Kepler's third law like you can with a spiral galaxy, but you can use, again, the virial theorem, a rewriting of the same basic physics, and figure out what is the mass in elliptical galaxies, and you can do that as you march outward through the galaxy. It's a little harder in ellipticals because their light falls off pretty rapidly. They don't drop off as conveniently gradually as does the light in a disk of stars like a spiral galaxy. But you can do it. Easier is using velocity dispersion. So what's the idea there? Well, if you lay your spectrograph slit across the image of a galaxy, okay, I was hoping I had a elliptical galaxy in the next slide, but I didn't. So you have to just imagine a big elliptical galaxy, and your slit has got some finite width inside your spectrograph, and it's laying across the image on the chip, the image of that galaxy, and it's going to let in the light of hundreds of millions of stars, not hundreds of billions like is in the total elliptical galaxy, but hundreds of millions anyway. And that's plenty enough to have a sampling of stars that are going towards you and away from you and sideways and every which way because they're all moving randomly. Think about the way the Doppler effect is going to change the position of the spectral lines corresponding to each of those stars. Now you can't get a spectrum of one individual star in an elliptical galaxy because they're way too dim, but you are getting the collected light of all those hundreds of millions of stars. And so basically what's happening is the Doppler effect is smearing out across wavelength each of those spectral lines. So if you look at the H-alpha line, it doesn't look like a nice sharp line. It's 656.3 nanometers wavelength. It looks like a broad, blurry, smear of a line. Kind of like instead of giving a nice fine pen line, you get more like the sideways swipe of an artist's soft, dark pencil of a line, and it's all spread out. And by measuring the width of those lines, you're measuring the Doppler broadening. You're measuring the velocities, the internal velocities inside that galaxy. And those velocities are caused by gravity, and the gravity is affected by the dark matter that's in that galaxy. So again, you can get the mass of elliptical galaxies by measuring its velocity dispersion. Probably worth remembering. The velocity dispersion. There's a buzzword for you. The width of the spectral lines. Now imagine that you could only get a blurry image of a really, really distant cluster of galaxies. Suppose your technology was so poor you couldn't even see individual galaxies. This isn't really true, but just imagine that were true. Then you could use exactly the same idea, Doppler broadening, measuring the width of spectral lines due to the collected light of all the galaxies in a cluster of galaxies. And the same idea would work. Luckily, we don't have to do that. We can see the individual galaxies, and then we can use the virial theorem. Even our own Milky Way is dominated by dark matter. There's the rotation curve. This is an old plot. I should probably find a new one, but it gets across the point. There's the rotation curve of our own galaxy. The velocity of rotation rises pretty rapidly, and then it kind of spreads out here. I think the actual number for the sun now is up a little higher than this, maybe more like 250. But the point is it's flat, okay? We got a flat rotation curve to well beyond. I mean, look at how far out this goes. Now you might be saying, but Rick, you told us the sun was about 2/3, 3/4 of the way out to the edge. How could you possibly measure stars way out here? There aren't any stars, Rick. And yeah, okay. So what we do is we take advantage of the fact that there's also cold hydrogen gas in the disk of our galaxy. Remember, that's how you make stars, is out of cold gas. And that gas goes out much further than the stars. And that gas turns out to have a spectral line in the radio part of the spectrum. The 21 centimeter line, it's due to a spin flip in the electron. It's something I don't really want to go into, but you can look that up, spin flip radiation. It's a nice convenient way to see, quote unquote, cold hydrogen. And so we can measure the wavelength of that and then get the velocity of that gas going around in a circle around our galaxy. And there it is. It doesn't go down to well beyond the position of the sun. So we are surrounded by a dark matter halo. Our galaxy is inside of a huge halo of dark matter. In some ways I like this graph, but in other ways I don't, because it looks like the dark matter just sharply cuts off here. And it doesn't. What it does is it's denser in here, and then it gets less and less and less as you go out, and less as you go out. So the shading could have been done better, and if I look through Google, or maybe you guys could Google and try and find me a better image, but I really like otherwise the way it shows the disk, it shows the bulge, and it even shows the globular clusters in the inner halo of our galaxy. But there's an outer halo that's not full of anything except dark matter that just goes on and on and on. Probably halfway to Andromeda. Okay, so now we get the fun part. So how do we figure out what the dark matter is? So when you're doing science, again, you want to obey Occam's razor, not just because Occam said so, but because you also have scarce resources of money, of graduate student time, and frankly your own career time, and also a little bit of urgency in racing to get the answer before somebody else scoops you on the great discoveries. And so you try to guess the right answer first. So you start with the stuff that could be easily tested and which you already know exists. Okay, so what could the dark matter be? So what we want to do, I mean, normally if we were in the classroom, I'd literally be asking you, and I would hope you guys would come up with ideas like, oh, Rick, could it be this? Could it be that? Could it be? And not go out into the wild blue yonder. Okay, we don't want to go to the wild blue yonder of blue flashing lights. Not yet. Okay, because that's what makes it fun. We don't go out there yet. Could it be gas? Could it be just plain old hydrogen gas? We know that hydrogen is 90% of all the atoms in the universe. Maybe there's just a lot we can't see. In fact, Rick, you've already just told us that there's cold hydrogen out there. Maybe it's just cold hydrogen gas. No, it can't be cold hydrogen gas. And here's the way you test that. You look at other galaxies that are past the dark matter halo. You take advantage of the fact that we have to look through the dark matter halo that we live in to see other galaxies beyond our own. So you can look at the Large Magellanic Cloud, which has some nice bright nearby stars. That's a good way to do it. Or you could look at more distant things if you want. But the LMC is plenty far enough away that it samples the large majority of the dark matter of our galaxies, near as we can tell. And you look for what? Absorption lines of hydrogen. You look for H alpha in absorption, H beta, H gamma. Or if you really don't think it's hydrogen, you could look for helium lines. Probably hydrogen, though, is the natural thing to look for. It's what the stars are made out of. The stars just formed out of gravity, out of the available stuff. If that's what you're saying the dark matter is the available stuff, it's almost certainly got to be hydrogen. Well, we look, and no, there's no absorption lines. I mean, there's a little teeny bit, okay? So we did say there's some cold hydrogen out there in the disk of our galaxy, but there's nowhere near enough to account for, roughly 90% of the mass of our galaxy, which is what we need. Could it be dust? So here's a dust cloud hiding background light. So how would you tell if you're looking through dust. And we talked about that. And we saw, and maybe you can even see in this slide a little bit, how the stars that are partially hidden in the dust are actually, well, I don't really know where this slide came from. I'm starting to wonder whether somebody just created it ad hoc. I think maybe there really is dust here. Can you tell how the stars are a little redder here? Now that star is red for a totally different reason. That's probably a red giant. But when you look at stars through a dust cloud, then it will scatter out preferentially the blue light. And it's the same phenomenon you see every sunrise and sunset. The sun looks redder because you have to look through dust, aerosols, smog, exhaust, sea salt crystals, whatever. Aerosols typically have wavelengths that are of order a few times, or maybe even less, of the wavelength of visible light. And that's true also of interstellar dust. It has a wavelength, it has a size that's of order a micron or so, and that means that it's about twice the wavelength of green light, about 3 times the wavelength of blue light, and that's sort of a nice preferential size so that it has a strong preference for scattering the blue light and not so strong for the red light. So you look for interstellar reddening. Dust would redden background starlight. So what you do is you look at other galaxies like Andromeda, maybe take a big patch of blue stars, bluish looking stars. You look at the spectrum, you say, I know what kind of spectrum that is. That's the spectrum of an A0 star. I see the collected light of all these stars averaging out to pretty much an A0 type spectrum, or an A5 or whatever. Okay, spectral types, we talked about those. And you say, well, I know what color an A0 star is. We see those in the night sky, and we know exactly what the color index is. And gee, the color index of this galaxy is a lot redder than that. So the spectrum temperature is hotter than the color temperature. I guess I must be looking through dust. That's how you test it. But there's no dust. Fails. So it's not dust. It's not gas, it's not dust. Okay? Well, could it be rocks? Small things, but a lot bigger than dust. Could it be asteroids? Could it be comets? No, and here's the reason for that. First of all, we do have to say that if they're rocks, asteroids, or comets, you would not be able to so easily directly rule them out as you could for dust and for gas. And the reason is because almost all of the atoms that make up rocks, asteroids, and comets is hidden beneath the surface of the rocks, asteroids, and comets, and therefore doesn't interact with light. So the interaction of each of these things with light, when they're this far away, is so tiny that you wouldn't be able to tell. They don't have enough gravity that you can use that. Frankly, that's another good test we're going to come to in a minute. But they're not small enough, not powdered up enough that they have enough surface area to interact with outside light to directly detect it. So you have to put on your thinking cap and do some indirect testing. And here's how the indirect testing goes. You realize that all of these things are held together by solid state forces. They're held together by the chemistry of heavy elements, or what we call in the business metals. Okay, they can't be made up of hydrogen and helium purely, because hydrogen and helium doesn't make rocks, asteroids, and comets. The large majority of the mass of each of these things is in heavy elements. So then we ask, well, wait a minute, there are stars out there. There's stars in the halo of our galaxy. We know what they're made of. We talked about that. They're POP2 stars. They're stars with no heavy elements. They're made up of almost pure, pristine hydrogen and helium that came right out of the Big Bang. But wait a minute, Rick, gravity works on everything. Gravity should pull together whatever's out there, including heavy elements. There's no reason that only the hydrogen and helium should glom together to make stars? I mean, if most of the matter of our galaxy is in metals, they ought to be most of the matter of the stars that are out there. And they're not. In fact, they're even a smaller percentage than what's in the disk, where there isn't so much dark matter. So it can't be rocks or asteroids or comets. So the same reasoning that rules out dust will tell you that there can't be basically giant dust gloms making these things out there either. Okay, well, what about heavier things? Things that are big enough to be self-gravitating. So we talked about how things need to be at least a half a mile across before they begin to have enough gravity that you can begin to notice it. And the bigger it is, the more gravity it will have. So gravity will affect things now in another way that allows us to test gravitational lensing. So now we're talking about anything, not just rocks and asteroids, but dead stars, dim stars, red dwarfs. We talked about how red dwarfs are most of the stars in the local neighborhood. They're almost certainly most of the stars in the whole galaxy. And if they're out there in the halo, they'd be way too dim for us to directly detect. Maybe they're just red dwarfs out there. Maybe they're dead stars. Maybe there's a whole population of massive stars that lived out there long ago and they all died, and now they're all just, their dead corpses are floating through the halo of our galaxy, and they're too small and too dim. Remember, white dwarfs are only the size of the Earth. Maybe it's white dwarfs. Maybe it's black holes. You know, you can even get more exotic black holes all the way down to, you know, smaller sizes than you could account for by the deaths of stars. Who knows how you make black holes? Maybe you could make them other ways. So we need a name for these. And the group of astronomers who decided to do the first big study on this, decided they would use their, I suppose, young and adolescent male thing and call them massive clustered halo objects, because they're in the halo of our galaxy. Machos. Okay, so their group came to be called, I suppose, with not a little bit of encouragement from themselves, the Macho Collaboration. So, yeah, the Macho Collaboration. And the idea here is that if a macho passes in front of a distant star, you will be able to tell. Now, you might first think that, oh yeah, I could figure out how that would happen. If it passes in front, we're going to see an eclipse, and the background star will disappear. So we could look for eclipses of stars in the, you know, the large Magellanic Cloud or the small Magellanic Cloud, or maybe if we're careful enough, even all the way out to Andromeda, we could look for eclipses. But I would say no. If you do the math, you'll find out that for things that far away, for throws that are that long, now we're talking hundreds of thousands of light years, then it is not an eclipse that you would look for. Instead, the gravity of these things, no matter how weak, is actually enough to bend the light a little bit, enough that you'll actually get more light into your telescope and not less. So it was chosen, I think pretty naturally and obviously, to use the LMC, the Large Magellanic Cloud. LMC. There's a picture of the LMC. So yeah, there are a lot of dim stars that just turn into a blur, but there's a lot of bright stars here too. And so what they did is said, here's what we're going to do. We're going to ask for a ton of telescope time, but they're going to give it to us because we're going to discover what is the dark matter. Any dark matter that is self-gravitating, we're going to be able to find it. So they did the math, they did the statistics, they said, you know, if there are dead stars out there and they have roughly a solar mass, and we know that the mass of the galaxy, from what we've measured, is about 1 trillion solar masses, and if most of that's dark matter, then how many machos is there, and how fast are they moving, and therefore how often should we see them pass in front of a star, and let's just get as many stars as we can on our CCD chip, and how often do we have to take a picture. And they worked out the numbers, and it turns out that, gee, you know, we could do this. This is doable. If we just take a picture, a couple of pictures a night of the LMC every night for a few years, we ought to see hundreds and hundreds of macho events as a macho goes directly in front of one of these stars. And what you would expect to see is that star to brighten. Now, the next question, though, you'd want to ask is, well, how long should the macho cause the brightening? Because if it happens in an instant, we're going to need to take like a video, and we don't have the hard disk space to do that. I mean, we could take 2 or 3 pictures a night, but we can't stare at them nonstop. That's just too much. Well, you do the calculations and you realize, you know what? These things move slowly enough out there that they'll stay bright, extra bright, for about a day and a half, 2 days, 3 days, something like that. That's reasonable. That means you're not going to miss them. You'll catch them. I mean, assuming you have clear skies where you are. And so you work those numbers into your statistics, and they did put together a pretty good proposal, and time allocation committee said, yeah, this looks good, let's do it. I know this is a lot of time, but you know what? This is the most important problem in astronomy, bar none. So yes, and you guys are the right guys for the job. You guys get to find what is the dark matter. So here's a macho event. There's a distant star. Obviously, we're zoomed way, way, way in. You can see the little pixelation here. We're zoomed way in, and then it brightens up, and then it goes back to being normal again. Now, part of what you have to worry about is the following, though. You might be saying to yourself right now, but gee, Rick, couldn't there be just plain old variable stars that are doing stuff like that? I mean, how do you really know it's a macho? All you're really seeing is a star that gets brighter and then dimmer. So you think about, well, what kind of variable stars are there? Well, there's eclipsing binaries. They wouldn't do this. They do the opposite of this. They're bright and then they dim briefly and then they come back. So it couldn't be eclipsing binaries. Well, what about Cepheids? Well, Cepheids go through a pulsation like this, okay? So they don't do this either. And most of the other kinds of stars that are variables are variations on the Cepheid theme. They're pulsating stars. There is one class of stars, though, that does do something like this. They are called flare stars, and they're normal, and then bloop, they get bright, and then they dim down again, and then they go back to normal. Flare stars. So we want to guard against getting fooled by flare stars. So what are flare stars? They're mostly red dwarfs that have deep convection zones and strong magnetic fields. And you can have solar flares on those that are way, way, way bigger than the solar flares that we see on our star. We're lucky if we don't have a star like that, because the flares here can brighten the star by a factor of 10 or even 100. And if the sun did that, well, it would, sterilize the Earth. We would be like those cartoon figures, who are holding a dynamite stick, and then a moment later they're all black and smoking. Yeah, so that would be us. We don't want that. So we could look for flare stars. How do we check and make sure that our machos are machos and not flare stars? So here's how you do that. Flare stars are dim and red. But when they flare, the light that's coming off that flare is very hot. It's very blue. And so the color of the flare is going to be very blue. So what you do is you take not one picture every night, but 2 pictures every night. And you do one in a red filter, and you do one with a blue filter. Now, what does gravity do? What would a real macho do? What a real macho would do is it would bend all the light. It doesn't care what the wavelength is. It all follows the geodesics determined by general relativity around that gravitating object. And so what you would get is a uniform brightening in red and a uniform brightening in blue and green and any other color you can think of. A very clean, easy test to make sure what you're really seeing is a gravitational lensing event. So the Macho collaboration really did their homework and they figured it all out. And they were very successful in carrying out the mission. Here's another macho. And they did see some machos. What did they find? The project ran from 1994 to 1999. 6 years of data, 12 million LMC stars. How many machos? 15, roughly. 15. But Rick, you said they were supposed to see hundreds and hundreds. Yeah. So what does that tell you? It tells you the dark matter is not machos. Okay, but the story's not quite done yet. There's another group. Of course, they needed a name that could be just as catchy, because you need a catchy name if you're going to get funded, right? That's half of funding, is getting a catchy name. I'm joking, I think, but anyway, you do want people to remember you. So they said, well, let's use the bold stars of the Milky Way. I mean, we do have Bada's window. We do have a little region where we can see the outer bulge of the Milky Way. We can get lots and lots and lots and lots and lots and lots of stars on one CCD chip, more than the LMC people could. And because we're towards the center of the Milky Way, and because the dark matter from our rotation curves does seem to be denser in the middle of our galaxy, and of course it's pretty hard to imagine why it wouldn't, no matter what it is, be denser towards the middle of the galaxy, they expected a much higher event rate. And they had much higher sensitivity, and so they should see lots and lots of events. So they got funded too, but they needed a good name as well. So the optical gravitational lensing experiment. So if you could be macho, you see, you could also be an ogler. Anyway, adolescent males, what are you going to do? Actually, they're a little older than adolescent, but they still got a little bit of that in them. But we all love that, right? Okay, so the Ogle experiment's actually still going on, or it was until, last I checked it was. 19 years of data, again, they confirm basically what the Macho collaboration found, and that is no, there's nowhere near enough events. They did see some, but not enough. So we have good confidence now. The dark matter is not machos. There was a new study by Nakura et al. Came out just last year, and they've even been able to rule out low-mass so-called primordial black holes through gravitational lensing of stars in the Andromeda Galaxy. So we've ruled out all forms of ordinary matter, from atoms all the way up to elementary particles of, well, atoms are made of elementary particles. So let's say atoms glom together to make molecules. So you can rule those out with absorption lines as well. Dust. So now we're talking about little bits of hundreds or thousands of molecules glommed together. And then up to rocks, and then up to asteroids and comets, and then up to planets. Planets are self-gravitating. The Macho collaboration would have found those. To dead stars, red dwarfs, white dwarfs, you name it. We've ruled out all forms of ordinary matter. We've gone up the size scale from the smallest to the biggest, and we've ruled them all out. They all have observational consequences, and we've checked it out. So now it's time to get out into the wild blue yonder, and now it's time to get crazy. So the dark matter then must be made of something that, well, it certainly interacts by gravity, and we can hope and think and postulate that it might also experience the weak force. So maybe it is a weakly interacting massive particle, or a WIMP. So you might have liked to think that the dark matter was made of machos, but instead it looks like we're dominated by WIMPs. How humiliating. Bummer. But there's more bummerdom to come, because there's only one WIMP that we know for sure actually exists in nature, and it's the neutrino. and actually it was realized as far back as the 1980s. And the guy who employed me is a postdoctoral fellow, Simon White, very good astronomer, a great theorist, and contributed a lot to observational astronomy as well. And he studied back in the 80s, back before I ever met him, the consequences of a universe dominated by neutrinos. And here's the thing about neutrinos. Neutrinos, they move really fast. So we have to talk about a different way of classifying the dark matter before we go further. So there's a different strategy for finding out what is the dark matter. And the strategy is talk about, in effect, the temperature, the speed, the motion of the dark matter. So we say that either the dark matter is hot, meaning it is moving very rapidly, it was born, and it still has a very fast velocity, or it could be cold. Cold dark matter would be made of something that only has velocity because it's been pushed and pulled around by local gravity. But it was born with essentially no velocity and then just acquired some by being in a galaxy or in a cluster or something, and so it might be moving at speeds that are typical of stars, for example, but not moving at the speed of light, okay? Or something in between. We could call it warm dark matter. And whether it's hot, cold, or warm affects how structure forms in our universe, in our whole universe. So we're going to now talk about hot dark matter, cold dark matter, and warm dark matter. And to bring me into a little bit, we'll even talk briefly about mixed dark matter, because there's a story there. So hot dark matter is particles that have a high random velocity, in addition to the normal expansion with the rest of the universe that we talked about, the Hubble flow, and any galaxy or any velocity that they were born with. That's hot dark matter. Okay. Yeah, okay, I'm just going to move on. So, what hot dark matter candidates, elementary particles, could there be? Well, you could perhaps come up with other candidates, and you could go crazy there, but you don't need to, because we already have one, and we know it exists, and we already know that the dark matter can't be hot, just to cut to the chase. So, the neutrino is hot dark matter. They're very, very high energy, and yet they're extremely low mass. The current estimate on their mass is somewhere in the, the range of 1/10 of an electron volt, or maybe less. There's different kinds of neutrinos. There's electron neutrinos, there's muon neutrinos, and there's tau neutrinos, and they're all zipping around. Could they make the dark matter? And here's how you realize that no, they can't be. So these are moving at speeds that are so rapid that the only things that could begin to separate themselves out from this expanding early universe, the Hubble expansion that we still see today, is things that were so big that the free streaming of these neutrinos couldn't outrace it. So things like things on the size of large clusters of galaxies, or even clusters of galaxies, or so-called superclusters. We haven't talked about superclusters, but if you look off in the sky, you can see that, gee, there seems to be more clusters of galaxies in this direction and not so many off in that direction. And it does look like superclusters statistically do exist, although the statistical clumpiness of them is pretty weak, but they do seem to exist. These would be the first things to separate out. And then only later, after velocity sorting had kind of had all your neighbors moving at roughly the same speed as you are, or they wouldn't still be your neighbors, would have the local speeds, and compared to your local standard of rest, be slowed down enough that maybe then you could make a cluster of galaxies. And then only later within that cluster of galaxies could velocities get low enough from the dark matter, which again is what the dominant matter is, be slow enough to make individual galaxies. And then only then, within individual galaxies, could you hope to begin to make stars. So in a universe dominated by hot dark matter, the youngest things, the things that formed yesterday, would be stars. And the oldest things would be the superclusters. And if they're very, very old, then they would have plenty of time to get very density contrasty, to show themselves by being very, very clumpy. And stars would only just be beginning to form out of the gradual gas and dust in the galaxy. Okay? So this is a so-called top-down scenario. Structure built chronologically, from big down to small. Now, how does that compare with the actual universe? It is in violent contradiction. This is not at all the way the universe really looks, not even remotely close. The universe we see is dominated exactly the opposite. The oldest things that we can see are stars. Okay? I mean, we're not going to go back to the first few years of the Big Bang. We'll do that later. But again, we looked at globular star clusters, and we looked at the stars inside dwarf spheroidal galaxies, and those stars, those clusters are almost as old as the whole universe, 13.7 billion years old. And galaxies even are pretty clumpy, so they formed relatively old as well, 2 billion years after the universe itself. It's the clusters that look not very clumpy and the superclusters that are barely detectable at all. So we live instead clearly in a universe that is built bottom up. It's the densest, well, the smallest things are the things that formed first, and the biggest things are the things that formed last. And that tells you that the universe is not dominated by hot dark matter, it's dominated by cold dark matter. Okay? So there's the key thing, first key thing, or certainly a key thing to remember about dark matter. Whatever it is, it's cold. It is cold dark matter. Some people still try to see whether we can maybe squeeze in a little bit of warmth there, but frankly, even that is looking less and less likely, as well as being theoretically a little bit ugly. We don't need warm dark matter to account for everything we see. We don't know of any warm dark matter candidates. We want to be diplomatic. We want to be open-minded. We want to keep the door open a crack just in case. But, to tell you the honest truth, which we always tell you to do, give you the correct, best probabilities of what's true and what's not, and the probability of warm dark matter looks pretty low. I would not bet much money on warm dark matter. Cold dark matter. It's also nice and simple. We know that it has to be pretty darn cold. We know it's out there. And so maybe the universe is actually simple here, and there's really just one cold dark matter particle that is accounting for all this. So I use the word particle. Do we really know it's a particle? Well, at least it's not big enough to be self-gravitating. And if it only feels the weak force, it's hard to see how it could be clumped together and bigger than anything other than an elementary particle. So the candidates we're going to begin to look at are really elementary particles. But they're elementary particles that are not hot dark matter. They are cold. Okay? They acquired their velocities by being pulled on by gravity over the 13 billion years that we've been hanging around out there and getting clumpy. Okay, so here's the problem, though, with cold dark matter. There aren't any cold dark matter particles that we know for sure actually exist. I know, that sounds terrible. And it is kind of terrible. But you have to turn that frown upside down and say, well, gee, that makes it a nice mystery. Now we've got a mystery to solve. We can figure it out. Now, back when I was working on this in the 1990s, all of my compadres and I too would have thought, gee, what do you think? By 2020, are we going to have discovered what the dark matter, the cold dark matter is? I think all of us would have put some money, a little bit of risk capital on, yeah, we'll figure it out by then. Technology's getting way better, and we got some ideas, and we know how to test them. We're going to be doing the testing. Yeah, we'll figure it out. I'll bet you. I'll bet you we'll know what it is. Well, here we are in 2020, and, well, I'll save that for later, whether we know what it is or not. Now, it's going to get pretty wonky from here. I might have to go over a lot of purple slides. There's a limit to how much I'm going to expect you to know on the details of these, but, it's a pretty interesting subject. Okay, let's put a slide in here on warm dark matter. So what is warm dark matter? It would be something that has some primordial velocity, enough to kind of blur out the smallest things that we know are dominated by dark matter. So the smallest things we know that are dominated by dark matter are the dwarf galaxies, the dwarf spheroidal galaxies. But as near as we can tell, the structure of the dark matter, as revealed by the velocities of the stars in those clusters, still fits pretty well with cold dark matter. There was a time when we thought maybe we needed a warm dark matter, but in fact it was just a limitation in our technology and our ability to detect these things. There was a thought, and there's still a few people who are thinking or hoping, let's say hoping, that maybe there's warm dark matter, and the evidence would be there aren't enough dwarf spheroidal galaxies. But now remember how you make a dwarf spheroidal galaxy. This is from the last chapter. And the way you make them is you have stars and gas and dust mostly gas and dust come together and make some stars, but then some of those stars are massive and they blow up as supernovae. And because the mass of these things is so weak, even with the dark matter, is so weak that they actually blow apart. And all of the gas and the dust gets blown out. And that shuts off your star formation. So now you have very few stars. So it's pretty natural that there would be a minimum. It's about 10 to the 8th, about 100 million solar masses, that you would expect to see stars at all in these things. And below that, you'd expect that even the first generation of stars would be so inhibited by this mechanism that you would just not be able to find them. So warm dark matter doesn't really have a strong case for it at the moment. Okay, so what is a dark matter? Well, we think it's some elementary particle. So we just talked about that and why we think that. How can we try and detect these things? Could we detect them directly from the ground here? Or do we have to go out into space to try to find them? Well, there is one place where we're trying to discover them, and that is in the most powerful particle collider, okay, the Large Hadron Collider, the LHC, at CERN in Switzerland and France, kind of both at the same time. It's a big detector. And we're trying to see whether we can create cold dark matter candidates. Okay, so we need some candidates, though. Let's talk about what are the candidates for cold dark matter and explain the constraints that limit us to these candidates. The constraints. The particles have to be essentially dissipationless. So what does that mean? That means when they fall together into a gravitating thing, they can't squish against something and then just parachute themselves down to the middle. They may have been born with low velocity, but if they acquire some velocity by gravity, they're not going to be able to get rid of it. So you would expect then that the density profile would show a roughly 1 over r squared fall off. And that would tell you they're essentially dissipationless. They're not like hydrogen. Hydrogen bangs into other hydrogens, might form a H2 molecule that'll dissipate some of the energy of the collision, might form ionized hydrogen, but then you've got some radiation that's going to go away because their charged particles are going to wiggle the electromagnetic field, and that's going to carry energy away, and so again you're going to be able to dissipate. And that's how the gas in the disk of our galaxy formed, and that's how the giant black hole in the center of our galaxy probably formed, is through dissipation like this that enabled a lot of mass to get into a very small place. But we don't see it getting into quite that small a place at the amounts necessary. The fact that it falls off gently, relatively gently, like that, is telling us that it's probably dissipationless. It looks like it only feels the weak force, if that, and gravity. Doesn't feel the strong force, doesn't feel electromagnetism. Okay? Now here's some direct evidence for dissipationless that is on a bigger scale, and this is called the bullet cluster. And the two colors here are, the colors are added artificially later, but the meaning of the colors goes like this. So this is two clusters. A relatively big one here, clusters of galaxies. And these two clusters have run into each other. So this guy here, he came from over here. He came in like this. And this guy, he came in from over here. I'm going to draw him from off center a little bit just so I don't put line on top of line. Okay? And so these guys actually went right through each other. Now you might say, well, how could they do that? Well, you know what? There's enough empty space that all the individual pieces, the stars and even the galaxies for the most part, they didn't run into each other. They just passed each other like, kind of like on those freeway chase scenes, and Terminator and other movies where you're going the wrong way down a freeway and somehow you still manage to miss all the other cars. Of course, that's all CGI, but anyway. So where was I? The blue. Okay, the blue is trying to tell you where is the dark matter. This is the color demonstration of the mass distribution, which again is more than can be accounted for by all the stars. There's not enough mass in starlight and cold gas would also get blown backwards. But there's not enough mass in stars. The dark matter went right through. So the fact that there's a blue clump here, just as big as this cluster, and a smaller blue clump here, is telling you that the dark matter went right through each other and they didn't bat an eye. They didn't get dissipated at all. What did get dissipated is the gas. And that's what this is. This is now heated gas, the red. And it did feel each other, and so it did get knocked backwards. There's even a bow shock here, it kind of looks like. Okay? But the dark matter is not the gas, okay? Clearly these guys are way offset. So the bullet cluster argues that, yes, the dark matter is dissipationless. It needs to be stable. Here's another characteristic. Or at least stable enough to last for 13 billion years without disappearing. The stability of the proton is something we can now measure. The stability of the proton can be measured in a very interesting way. Take enough water, which has protons in it, and get enough water there and enclose it in a big dark sphere and put a whole bunch of very sensitive light detectors inside the sphere and wait for one of those protons to decay. So when it decays, it'll turn into lighter particles that are zooming off at the speed of light. It's going to create Cherenkov radiation that's going to create light. Light from inside something that is absolutely opaque and won't let any light in. And that's how we detect the decay of protons. Now, 10 to the 34th years, you might say, Rick, the whole universe is only 10 to the 10th years old. How could you possibly measure the age, the lifetime of a proton to that kind of level? That's impossible. No, it's not, because this 10 to the 34th years is a random thing, just like all radioactivity. It's a totally statistically random quantum process. So all you need is to get 10 to the 34th protons together in one place, and you ought to have one of them disappear every year and see it produce Cherenkov radiation once a year. And then you could measure. And if you work it out, that's about what we got with the big Sudbury neutrino detector. It's there to detect neutrinos, but you know what? It could also measure the decay of protons. And if you go through a whole bunch more math, then you can even convince yourself that the standard model of particle physics looks like it has no new forces. The four forces of nature, that looks like all the forces we got. If you go back early enough into the early universe, maybe those unify into less forces, but it doesn't look like we have more. So the particle looks like it's got to be stable. Oh, so by the way, yeah, just to finish that, no, we haven't seen the proton decay. It's at least 10 to the 34th years between proton decays. Okay, wait a minute. The particles have to be cold, or at least cool. And we really already talked about that. Well, there's additional evidence we haven't talked about yet. Gee, we're only 3 minutes away from the end of class. I will continue for another 2.5 minutes. Clearly, we're not going to get through all this chapter, but then you know what? I didn't expect to. We do pick this up next time on Wednesday. But we're going to look at the CMB, the cosmic microwave background. We haven't talked about that yet, but the cosmic microwave background encodes the lumpiness of the universe back at a time when the universe was way younger than anything born in our galaxy, way younger than the globular clusters that we've already talked about. And the lumpiness there is also telling us how cold is the dark matter. So, being cold allows the particles to gravitationally clump on all scales, even scales much smaller than typical galaxies. And we're going to see that the universe must have been lumpy, even back at 300,000 years after the Big Bang. And there's no way that the ordinary gas that makes up the stars could have been that lumpy when it was that early, because it was still too warm to do so, and there wasn't enough time for that gas to have gotten clumpy. The gas must have fallen into clumps and lumps that were already there, lumps that were made by the dark matter, which doesn't dissipate and doesn't need any kind of help. It just falls together, and it can be the lumpy stuff right away, and the ordinary stuff falls into it, and it makes the microwave background lumpy. That's where we're gonna reiterate that again next time. But it is now 10:50, so I am going to close this program. So this is good. We got in good 73 minutes. That'll make a nice, good YouTube video. I hope other people around the world and on other stars and galaxies who can access our internet will enjoy this presentation. I think it went pretty well. Does anybody have any last questions before I start shutting things down here? Sarah, Andrew, Abriel, Riley.